So question number 2. If the current temperature of an object is T0, so T0 is the current temperature of the object, and the room temperature is TR, so TR denotes the room temperature, Newton's law of cooling states that the rate of cooling of an object is proportional to the temperature difference between the room temperature and the temperature of the object. So for part A of this problem, write a differential equation and an initial condition whose solution would describe the temperature of an object as a function of time. So let's have a look at part A of this problem. So here's part A. Now let me define capital T to be the temperature of the object. So I'm going to let capital B be the temperature of the object, so capital T is the temperature of the object at a time small t, whereas T0 is the current temperature, okay, and TR is the room temperature. So note the distinction between the terms capital T, which is the temperature of the object at a time small t, whereas T0 is the current temperature of the object and TR is the room temperature. So going back to this sentence, so Newton's law of cooling states that the rate of cooling of an object, so by this term rate refers to d by d small t, so rate relates to d by dt, where small t refers to time. So let's create an equation. So we have d capital T over d small t, okay? And that is proportional to, the temperature difference. So difference relates to a subtraction, but it's the difference between the room temperature, so room temperature refers to TR, so remember the room temperature is denoted by TR, and the temperature of the object, so the temperature of the object meaning capital T. So remember we've defined capital T to be the temperature of the object. Now let's get rid of this proportionality sign. So to get rid of the proportionality, let's equate. So d capital T over d small t is equal to k, so k is our proportionality constant, k into TR minus capital T. So let me just say that k is our proportionality constant. So let me define that in the corner here. And so as you can see, we wrote a differential equation, but we also need to write down the initial condition. So initial condition means what happens when t is equal to 0. So small t referring to the time. So when t is equal to 0, we can say that the temperature of the object, meaning capital T, is going to be the current temperature. So the current temperature is denoted by T0. So just to repeat, initial condition means the condition relating to what happens when the time is 0. And when the time is 0, it's plain to see that the temperature of the object is the current temperature, T0. So here is our initial condition. So that completes part A of this problem, and let's have a look at part B. So for part B, let's have a read. So let us consider a 95 degree C coffee cup that is in a 20 degree C room, and we need to assume that the proportionality is 1. So the proportionality meaning the proportionality constant is 0.1 rather, so it's 0.1. solve the differential equation in part A. So we need to solve this differential equation to find a function describing the temperature of the coffee as a function of time in minutes, and we need to use the solution to estimate the temperature of the coffee after 20 minutes. So let's assume that this 95-degree coffee cup, so the 95 degrees C in particular, is T0, the current temperature of the coffee, and TR, the room temperature, is 20 degrees C. So let me pick up my pen and let's gather some data. So if I use this page over here, second page, so let's have a look at part B. So let's say that T0, the current temperature of the coffee, is 95 degrees C, and we have the room temperature 20 degrees C. So we have the room temperature, so room temperature is denoted by TR, remember, that is 20 degrees C. I think we also been given the proportionality, so the constant of proportionality value is 0.1. So K in this case is 0.1. And we need to solve this differential equation here. So let's solve it and let's find a function describing the temperature of the coffee, i.e. capital T. So let me copy out this solution. So we have d capital T over d small t, and that is equal to K, and within the bracket TR minus T. So TR minus capital T. Now I'm going to plug in this data right at the end. However, let's solve this differential equation. So I'm sure that you would agree that this is a first order differential equation, and to solve first order differential equations we need to use the method of separating the variables. So by separating variables, so bearing in mind TR is a constant, that is the room temperature, capital K, or K, is a proportionality constant. Let me bring the TR minus T though to the left hand side. So retaining the d capital T on the left, I'm going to have 1 over TR minus capital T d capital T, and that is equal to, keeping the constant K on the right, however bringing the d small t to the right, d small t. So I've separated the variables, and let's integrate both sides. So if we integrate, so let's move on to the next step, let's integrate both sides. So let's integrate the left, so we have 1 over TR minus capital T, the temperature of the object, with respect to d capital T, and we also integrate the right, K, with respect to small t. Now let's integrate the left hand side, so we can integrate the left hand side. So if we integrate that, we'll have minus ln TR minus capital T. So that is what you should have when you integrate the left hand side. Okay, and when you integrate the right hand side, you'll get K small t, but be sure to add an integration constant as you're integrating an indefinite integral. Now I don't like this negative in front of my ln. Let me get rid of this negative. So let me multiply throughout by -1. So if I multiply by -1 both sides, we'll have ln TR minus capital T, that is equal to minus KT. So even integrate the even multiply the right hand side by -1, so you get -1 times KT minus KT minus 1 times plus C minus C. And let me rearrange this. So let me rewrite this. So in this case, let's rewrite in the form TR minus capital T. So TR minus capital T then will be e to the power minus KT minus C. And if we go one more stage, so if I separate this exponential to give me two terms, so let me illustrate what I mean. So on the left I still have the TR minus capital T term, but on the right, if I separate it to give me e to the minus KT times e to the minus C. So in other words, I'm using the multiplication rule of indices to rewrite this exponential term into two terms. So remember the multiplication rule: whenever you multiply two terms having the same base, we add the powers. And if I rearrange in terms of capital T, so in other words, if I bring the capital T to the right, and if I bring this whole term to the left, we're going to have capital T then. So that is equal to TR minus e to the minus KT times e to the minus C. And if I go one further stage, now e to the C is a constant as C is a constant. So if I pick up a different coloured pen, let me choose red. So if I replace the e to the minus C by another constant, so I'm going to choose the letter capital D. So if I let capital D be e to the minus C, I could rewrite this equation as capital T, that is equal to TR minus, so e to the minus C, let's replace that by capital D to give me capital D e to the minus KT. Now let's calculate this constant D. Now if we go back to the question, we've been given the current temperature of the coffee as 95 degrees C, and the current temperature refers to the temperature at the time t equals 0. So if I plug in the data, so if I use the data that when t equals 0, capital T, the temperature of the object, equals the current temperature, which is 95 degrees C, but instead of using the 95 degrees C, let me use T0 instead, so where T0 is the current temperature. So if I plug in the data, capital T, which is T0, that is equal to TR, the room temperature, minus D e to the minus K into small t, which is 0. Now, minus k times 0 is 0, and e to the 0 is simply 1. So let me rewrite this as T0 equals TR minus D times 1, which is D. So therefore, D in this case is going to be, if I bring the minus D to the left hand side and the T0 to the right, so I'm going to write my D as TR minus T0. So that is an expression for our constant capital D. So this is a capital D. Let me select a different coloured pen. Let me use this purple pen. So I'm going to replace D in this previous equation here. So if I go and go back to my favourite colour, blue, so when I do the replacement, capital T then is going to be TR, so TR minus capital D, which is TR minus T0, multiplied by e to the minus KT. So here is the temperature of the object capital T in terms of TR, the room temperature, T0 is the current temperature, small t refers to time, and K is our proportionality constant. Now, if we go back to the data that we wrote down earlier, we know T0, the current temperature, that being 95 degrees C. So that comes from the question, remember. We know TR, that's the room temperature, 20 degrees C, also from the question. And we know K, the proportionality, 0.1, that is from the question also. So if I replace this data into this equation or this function for capital T which we have, so if I pick up the blue pen, we're going to have capital T, that being TR, which is 20, minus TR being 20, minus T0, that being 95, e to the minus K, which is 0.1 into small t. If we simplify this, we're going to get 20. 20 minus 95 is minus 75. Minus 75 times this minus in front is plus 75 e to the minus 0.1 t. So here is the temperature of our object capital T as a function of small t, the time. But we're far from finished, because we need to use this solution to estimate the temperature of the coffee after 20 minutes. So 20 minutes refers to small t, the time being 20. So let's plug in t with 20. So let's replace t by 20 in our solution here. So when t is equal to 20, so capital T, the temperature of our object, is 20 plus 75 e to the minus 0.1 multiplied by 20. And this is where the calculator kicks in. Roughly, I would say to one decimal place, 30.2 degrees. So 30.2 degrees C. So that being the temperature of our coffee after 20 minutes. So I'm sure that you would agree, safe to drink. So in this case, this is how that example is done. So that is another example of modelling with first order differential equations. So I hope you enjoyed this problem concerning Newton's law of cooling. And if you did enjoy the video, if you did like how the problem was solved, be sure to subscribe, and I hope to see you again. Thank you.